Okay, I didn't realize that the video timer was timing out on that last slide. So, pick up where I left off was we were talking about the spectral classification of stars, ordered in terms of OBAF GKM. And this also corresponds to temperature, which we'll see in a little bit. So you can remember this by knowing that the O-type stars are the hottest, and the cold stars, the M-type stars, are there on the right. So our sun is about a G-class star. So these are further classified from 0 to 9. So 0 is hottest, 9 is coolest. So if you had an O0, that would be the hottest of the hot. And A0 would be the hotter end of the A classification, and so on. So this spectral classification corresponds with temperature sequence. So your hot stars, like your O and B stars, are like 20,000 degrees Kelvin, and your cold stars, like your M class, are like 2,000 degrees, 3,000 degrees Kelvin, and so forth. Now, some stars have temps that are even lower than the M class stars. Now, a lot of these are not really stars at all. They're called brown dwarfs. And they're too small to sustain thermonuclear reactions in their core, so they're like almost stars. And they glow from heat contraction. So they're cold, and they're best observed with infrared telescopes. And so they have their own classification on the spectral class. They're called L and T type stars. Okay, so really there's like two more classes on here, but the main ones are O, B, A, F, G, K, M. So now that we can know the luminosity and the temperature, we can figure out our last stellar property, which is the size, the radius. So notice here that luminosity is proportional to surface area times temperature to the fourth. So surface area is if you try to wrap the star in wrapping paper, okay? That wrapping paper, if you took the area of it, that would be the surface area. So surface area of a sphere is 4 pi r squared. So that means that the luminosity then is proportional to the radius of the star squared times temperature to the fourth. So for a given luminosity, the greater the surface temperature, the smaller the radius must be. For a given surface temperature, the greater the luminosity, the larger the radius must be. Okay, so when we start thinking about temperature, radius, and luminosity, we really have to consider all three. So you're going to do some worksheets for your activity this week that are really going to cause you or help you to dive in and consider all three of these at once: the luminosity, the radius, and the temperature. Okay, so here we have it all mapped out. So we determine the distance through parallax, okay? And using distance in combination with how bright a star appears to be, we're able to determine how much energy is really coming from the star, its luminosity. From looking at the stellar spectrum of the star, we're able to determine surface temperature. So combining luminosity and surface temperature, we're able to figure out how big stars are. So that's how astronomers figure out the properties of stars. Now, if we take all the stars in the night sky and we look at their stellar properties, their luminosity, their size, and their temperature, and their spectral type, and we plot them, they plot out into groups. So on the left here, you're really looking at just stars in the night sky. We plot them, and they plot within these different regions. And we plot this on what we call the HR diagram, which stands for Hertzsprung-Russell, the two founders of this diagram. This diagram might be one of the most important diagrams in astronomy, because what it is looking at purely just stellar properties. We just map up the stellar properties, and they form into these groups. And what we'll talk about next week is that these groups are groups of stellar evolution. So we're actually looking at stars at different stages within their stellar evolution. So when we plot these stars, they end up forming four main groups: the main sequence, this long one here, the supergiants, the giants, and the white dwarfs. And each of these groups represents different stages in stellar evolution. So the main sequence is where stars just start to form, meaning that they've just started thermonuclear reactions of hydrogen, and where they burn all their hydrogen. So stars live out most of their life, like 90% of their life, on the main sequence. As they start to die and they stop converting hydrogen into helium, they move off this branch and into the supergiants and the giant phases. The white dwarfs is the dead core of old stars. Okay, so we're really looking at the different time scales of stars. So notice that this plot is a plot of luminosity to greater luminosity at the top, lower luminosity at the bottom, versus spectral type, and on top, temperature. Because remember, spectral type and temperature go hand in hand. So notice on this plot over here, it's surface temperature. So M stars being cool, O and B stars being hot, low luminosity to high luminosity, and here we're plotting absolute magnitude. So for example, notice our sun, 1 solar luminosity, because these luminosities are luminosities compared to the sun. So 1 solar luminosity, our sun is down here at about 5,800 degrees Kelvin. It's about a G-class star, okay? So if we wanted to say if we had a really bright, a really high luminosity star and a high temperature, we might be up here in the main sequence. If we had a really high luminosity star but a low temperature, we might be over here in the supergiants, okay? So I did briefly mention that parallax was really only good for distances close by, within 100 parsecs or so. So pretty far, but not all stars. So if we have very distant stars, how do we figure out their distance? Well, let's back up to what we know. Okay, so if we know the spectral class, we therefore know the luminosity class and the spectral type and the surface temperature. We plot all that on the HR diagram, therefore we know the luminosity. Well, if we know the true luminosity, and we know how bright it appears to be, we therefore could figure out the distance. Okay, because if we know the true luminosity, and we know what it appears to be in the night sky, we can compare it to other stars and figure out how far away it is. So it's not necessarily the best method, but it's what we've got right now. Okay, one other really cool thing about looking at stellar properties is if we look at the luminosity of stars versus the mass, we'll notice that as stars are more and more luminous, they have higher and higher masses. So this is for main sequence stars. So stars on that main sequence, high mass means high luminosity, while low mass means low luminosity. Okay, we're going to find out next week that mass is one of the most important properties of stars, because mass really determines how long it lives and how it lives out its life. Okay, so that concludes how astronomers know what we know about our stars.